I will travel where no man has dared to go.
The accepted laws of physics break down.
Boundary between the known universe and a place beyond the reach of science.
Alright, hello everyone, and welcome to Forces on an Angle and Friction. So, just like when we are working with forces acting on an object on a flat surface, we have to still look at the X and Y axes. Okay, we're still going to be concerned with that, but now what we're going to do is we're actually going to move the X and Y axes to fit the same angle the box is at. So if you can look at it in that manner, like we're just kind of making it a little cockeyed and lifting it up, you should be fine with this. It's not much of a change. Okay, so let's see. This will be a step-by-step instruction. There's about several steps to it. It shouldn't be this hard, but you can watch it over and over again. Alright, so here's our scenario. A 10-kilogram box sits on a 35-degree ramp. The two materials create a 0.25 coefficient of friction. So as always, first thing we're going to do is we have to get a drawing to give us an idea of what we're doing. So we're going to go ahead and we're going to draw our ramp, and we're going to place our box right on top of it. Now, the one thing to remember is, as always, gravity doesn't care that it's an angle. Gravity is going to pull it down. Okay, so we have to consider that gravity is still pulling it down, but it is sitting at an angle or theta of 35 degrees. So we can calculate right away just our standard measurement for weight or the force of gravity by just taking the mass that we know of, the 10 kilograms, and multiplying it by gravity at 9.8 meters per second squared. Because we are using or taking the axes and the X and Y axes and also moving them to be 35 degrees to make it easier, we're not going to worry about a negative. Okay? Maybe later on if we go into more complex portions, but this isn't really focused on too much going the difficult math route. We're going to stick with the concept of what we already know of how everything's working. So once we have that done, okay, we're going to go to the next step, and that is finding the Y components. Okay, and of course the box is actually pushing down right on the ramp. So we know that if it pushes down the ramp as normal, that we're going to have a force normal. Okay, that's going to be pushing back from the ramp. Now, of course, the force normal and the force that's pushing down on it have to be equal. So they have to give a force net of 0. Otherwise, the items will just once again float away. If we say the force is too great. So once again, their force net has to be 0 on that Y that we're tilting. Okay, so we will know then that our next item, since we have the force of gravity, but we're slightly tilting it to be pushed down and oppose the force normal, we're going to call this our force of gravity Y, FGY. Okay? Now, how do you go about calculating the FGY? The first thing is try and find the other triangles that exist here. If you look between FGY and the force of gravity, okay, you'll actually see that it creates a right angle. See that? So the right angle exists in the air. So therefore, if that creates a right angle, we can realize that right underneath our object is actually theta. So it's 35 degrees on a ramp, but it just turns out that also it creates a theta right there, right underneath it. So 35 degrees is sitting right there in between FGY and FG. So just as when we first started working with 2D kinematics and vectors, we had to use the cosine sine function. So in this case, to calculate our FGY, it's very simple. We just simply take our cosine of theta times FG. That's all you do. And when you do that, you get FGY. Okay, in this case, we'll have a cosine of 35 times 98 newtons. And that'll give us an FGY, okay, of 80.2769 newtons. Okay, so the force of gravity is putting that much force, right? That much force on the actual angle on the ramp. So what happens to the rest of the force of gravity? Well, you just can't get rid of it. So the other part of the weight is actually going to be used towards the x axis. So that is what's going to give us our actual acceleration. And that's why if you have an object just sitting on a ramp, it slides off of it, because gravity is also using it in another direction. So we'll calculate that in a second. So if we know we have an FGY of 80.2769, once again, on the y-axis, it's not floating away, so our net has to be 0. So that means our force normal has to also match that same amount. Okay, so once again, our F net on the y, or our tilted y, is going to be 0. Alright, so now that we've calculated the y, we're going to go now to the component. So in the x component, what we have to realize, and you've seen this a billion times, if you place something at an angle, it wants to roll down. Even right now, you might have gone sledding, and the second you sit on that angle ramp on your sled, you just take off. And why? We have to realize, once again, friction is also pulling us down on our tilted x now, we'll call it. Okay, so we're going to call it our FGX. And our FGX, if FGY was cosine, then FGX is going to be sine theta times our force of gravity. So in that case, if we punch all those in, if we do sine of 35 degrees times 98, we get a 56.21 newtons of force, just being openly unopposed. So now, if we didn't have a frictional force, that's actually all we'd calculate. And that, if we wanted to find our acceleration, we would just simply take our mass of the object, our 10 kilograms, and we would go ahead and divide it, or we divide 56.21, or FG, we would divide that by our 10 kilograms. Because in that case, we'd have an F net there, so movement would happen. Because at friction, we have nothing opposing it. But in this case, we do have friction, okay? And it says that we have a frictional force of, or a coefficient of 0.25, which means that in that direction, right, it's going to be opposing it. So what we'll do is, to calculate our frictional force, we will take our mu, and so our frictional force is equal to the mu times our force of gravity on the y. Okay, our force of gravity on the y, because it's the y force of gravity that's actually in contact with the ramp. Remember, half of the force of gravity, or a certain portion of the force of gravity, is being pushed on the ramp, and the other force of gravity is being pulled down. So that's why we have our FGX and our FGY. So in this case, it's our FGY that makes contact with the ramp. So when we do that, we'd say it's 0.25 times 80.2769. Okay? When you calculate that, you punch it in your calculator, it should give you a frictional force of 20.069 newtons. Okay? Now that we have that done, now we realized before, right? Our force, we called it our force applied when we were on a flat surface, but in this case we're applying nothing. Gravity is doing it all. So our force of friction is trying to keep the object from moving, but the FGX is the force that wants to get the object to accelerate. So all we do to calculate it, for finding our net force, okay, that we're going to be experiencing, it is just our F net is equal to the FGX minus the force of friction, just like we did other problems before. Okay, we're just combining them together. Here we're going to know they're opposed, so we're going to subtract them, because we've tilted our x and y axes. So we have to use more of our logic than just vectors. So I'll take my 56.21 newtons minus my 20.069 newtons. Okay, when I do that, I get a force net of 36.141 newtons. Okay, and that's it. That's how you do these problems. So now if I was going to ask you from the beginning what is going to be the acceleration of the object, we would just look at this. And we go, okay, so we know our force net now, and we have our force is equal to mass times acceleration. So I take my force net divided by my mass, and that is equal to acceleration. And in that case, if I take my 36.14 divided by 10, I get 3.61 meters per second squared. Now below this video is going to be another video from another physics teacher that I was able to find. He handles the problem in a different manner because there's multiple ways to solve this. He does it more math-based, where you're actually crossing out variables and just simply doing calculations. He's doing more of a plug and chug method. This is more of a concept-based. So you can watch this and decide which one you like more. You might be more math-based, you might be more concept-based, but I'm hoping one of the two will definitely be something that can help you out and get you to understand how to calculate the forces on an incline. Thank you so much.
Millions zipping around our galaxy, nothing there to light them up. Millions and millions of black holes. Millions and millions and millions zipping around our galaxy, nothing there to light them up.
At the heart of a large black hole is a singularity. It's a point of infinite density. The accepted laws of physics break down.